Okay, hello everyone, and welcome to this Energy Institute webinar on the Good Plant Design Guide for CO2 stream impurity measurement, which was just published last month, so in May 2025, and is available to download from the Energy Institute's publication website. Welcome. Next slide, please. My name is Eva Leinwater. I'm the technical manager for CCUS in the Energy Institute's Technical and Innovation Department, and I'll be your moderator for today and introduce you to the Energy Institute and the CCUS program. I will also be joined by our three speakers, who are three of the main contributors to this guideline. Andy Brown, the engineering director at Progressive Energy, who was also the principal author and working group chair for this project. Gordon de Keyser, commercial and strategy director at Kim Process Solutions, and Manohara Godia Virabhadarpa, senior scientist at the National Physical Laboratory. They will present the document and expand on the rich and evolving topic of CO2 impurity measurement throughout this webinar. And towards the end, they will also be available for a 15-minute Q&A session. To start, a few notes on housekeeping. This webinar is recorded and will be made available after the event on our YouTube channel. All participants are muted except for the presenters. To post your question, so to contribute to the webinar, please use the Q&A function only rather than the chat function. So please have a look at how to make that change when posting your questions. Next slide, please. Before I hand over to Andy to kick us off, I will give you a brief introduction to the Energy Institute and our technical and CCUS work program. The EI is a chartered professional membership body for all people who work in the energy sector. We are a registered charity with a long history of over 100 years. The EI offers expert-led training courses, accreditation, professional development opportunities, including chartership for engineers, environmentalists, and energy managers. And the Energy Institute has 20,000 individual members and 200 partner companies in 120 countries. Our main purpose, as it's said on the slide before, is to accelerate the just global energy transition to net zero, both for our members and for broader society. Next slide, please. So how do we do this? We do this firstly through attracting and developing and equipping a diverse energy workforce, for instance, through professional membership and training courses. We also do this by informing energy decision-making through convening expertise and evidence, for example, through our flagship annual event, the International Energy Week, which happens every year in February, and the publication of the Statistical Review of World Energy. And thirdly, we also do this by enabling industry to make energy lower carbon, safer, and more efficient through our technical and innovation work, such as the CCUS technical work program, and also through our technical company memberships. Next slide, please. The Technical and Innovation Programme has an annual budget of £2.5 million, which is funding that we secure through the membership of our technical partners. This budget is then put towards developing technical resources, for example, guidelines like the one we're presenting today. We have 58 technical partners on board at the moment, ranging from major global energy companies, engineering firms to equipment manufacturers and others. And you can see them on this slide. Next slide, please. This very industry-driven approach enables us to be an independent custodian for technical expertise in the energy sector. And we use this role to develop 30 new technical resources each year with our members and in collaboration with external stakeholders, such as trade associations, regulators, and academia. These resources cover really a wide range of topics across the energy sector. So this includes the energy transition, for example, on CCUS or hydrogen, health, safety, and the environment, and also fuels and fuels handling. Next slide, please. As part of this broader technical and innovation work, the CCUS committee currently oversees 7 dedicated working groups who work on a total of 16 active projects. The main aim of the work program is to really address the scientific and technical challenges that CCS technologies pose and thereby to assist their deployment globally. And we do this much like the rest of technical and innovation by producing and regularly updating a growing collection of CCS documents. And in these documents, we aim for really high technical standard, which we are able to achieve through the much valued input from topic experts that sit on the CCS committee and who also participate in the relevant working groups. And another very important factor for us is collaboration with a range of stakeholders and experts from the CCS sector. The document that is presented today was developed by our CO2 stream impurity measurement working group. Next slide, please. This document on CO2 stream impurity measurement, this guideline, offers developers, operators, and regulators and others guidance on available and emerging technologies for measuring impurities in a CO2 stream, both online and offline, so in real time and lab-based. And it also offers insights into equipment selection, calibration standards, and the use of certified reference materials. And with that, I will hand over to Andy Brown, who will introduce us to the problems associated with impurities in the CO2 stream, as well as their measurement.
Thank you, Eva. Next slide, please. So I'd just like to start by providing a little bit of context here. Why would we want to measure the purity of a CO2 stream, given that all we're going to do at the end of the day is put it into a store, or perhaps to utilize it to make something else? And the reason for it is that the impacts of the impurities are significant because CO2 is not the same as natural gas, because it is an acid gas, where of course natural gas is not an acid gas. So we have to guard against the corrosion of carbon steel components. The impurities can lead to unwanted thermodynamic behavior in this fluid, because the CO2 stream can change very rapidly between gas phase and some sort of intermediate phase, which is between gas and dense phase, and of course in and out of dense phase. And the density changes are very large and that are difficult to control. The purity of the impurities within the stream can also lead to severe mechanical effects. And by that, for those of you who don't know about it, is something called running ductile fracture. And of course, any impurities in the CO2 can lead to degradation of the rocks in which it's stored. So it's important that we know what the impurity levels of the CO2 stream are. Next slide, please. So in order to minimize those impacts, there is a specification which will give us the maximum levels of impurity that can be tolerated by the downstream components. But because there is non-CO2 within the stream, that needs to be, as it were, balanced out when it comes to the commercial arrangements between the producer and the shipper and storer, because at the end of the day, people only get paid for the CO2 that they store. They don't get paid for the nitrogen. So this is looking at how we measure it. So on the right, there's a little diagram there. The fiscal metering in the middle there, that deals with the mass flow of the carbon dioxide. And just to the right of it, at that fiscal transfer point, that is where the impurities would be measured, so that what is going into the pipeline in this case is well and truly understood by the receiving party. Next slide, please. But there is a problem. When it comes to the practical ordering things, it's not always possible to obtain the equipment we need to measure these impurities. Firstly, because some of them are at very small levels, and secondly, that just because you can measure something in air, that doesn't mean that you can swap out the equipment and use it to measure the same impurity in a carbon dioxide environment. And we'll explain more about that as we move on. At this point, so the thank you. So we need to so the idea of this paper is to say, what is available now? What can we effectively go to the shops and buy? Where are the gaps? What needs to be done? And can we assign any priorities to it so that we can get at least in the UK, we can get the track one projects away. But what we discovered is that there are other people who are experiencing the same difficulties. So this isn't something which is unique to the UK. This is a set of problems which you will find in any CCS project anywhere in the world. So the first thing we have to do is to get the CO2 out into so that we can measure it. And Goddard de Keyser is going to explain to us what's involved in that, because again, this is not a simple process.
Thanks, Andy. And indeed, it's not. So we skip to the next slide. So I think so. It's knowing. So effectively, what is our task? We want to know the impurities that are present, but also in what fraction they are. And there are a couple of different tools that are available to us. That's offline and online analysis. That's also described in the paper. For offline analysis, what you do is you take an indirect sample. If you talk about either a manual sample, so at a specific point in time during the process, or an automatic sample, multiple samples over a longer period of time to get an aggregate view of of what has been passing through your pipeline. Or you can take an online sample, which allows you to get a fast answer and able to intervene into your stream. And it's probably a combination of the two that you need, because one is the offline analysis, and you see that to the right quite nicely. You can see you've got in spec normal production where you expect don't things are might not be fluctuating, but due to the effect of shutdown or startup conditions or changes in a factory or in a production facility, you can have times that you are out of spec. And those you also want to measure to make sure that as an aggregate, you remain within the impurity levels that you should be. So what you can do through an offline sample is you basically catch the samples under the conditions that they are in the pipeline, and that's very important because as we'll see later, conditions of bringing it back to the pressure and temperature that you can measure it under in the online analysis has a couple of drawdowns or risks of actually changing the actual composition of the gas or the fluid that you look at. The advantage of the online analysis is that really allows you to continuously monitor the stream. And if it changes, then make interventions. It's important to recognize that even though it's fast, there is still a cycle time dependent on the type of equipment you choose and the specific fabricator that provides it. Okay, so let's move on to the next slide. So what I want to do is basically provide you three big rules for representativity to make sure things that you really should consider when you design such a system from a representativity point of view. And the first is homogeneity. Basically, what you want to get is a mixture that is homogeneous at the point where you're taking it out of the pipeline. Even we're talking about fluid and gas, and often the expectation is that they behave as a homogeneous stream. But even in gas phase, there can be droplets, there can be differences in density, and in liquid phase, you can see the same effects. And if you don't take those into account, you might not take out a representative sample of what flows through the pipeline through time or at a specific moment in time. The second is isokinetic. So at the point where you take out the sample, you have to really take a lot of care in how you take it out and extract it in terms of the design of the probe itself, but also the whole the tubing and piping behind it. And particularly, and that's the next phase when you start to condition it to bring it down to the pressure and temperatures that these analyzers can actually measure it, which basically lead to phase changes and then effects like adsorption, desorption, absorption, which can basically change the actual composition of the gas or fluid and therefore give you a distorted view of what's actually happening in the real process. Okay, so let's move to the next slide. So we start with homogeneity. If you look to the ISO or API standards, a sampling point should be at 1/3 of the diameter of your pipeline. And you see that nicely illustrated to the right. So that means at that specific point, through time, you want to make sure that that specific point is representative of the entire stream. So what that means is that basically and that you see at the bottom quite nicely illustrated with different types of behaviors, in this case of a fluid. You can have different types of behavior dependent on the density, slugging, annular flow, bubble flow, wavy, plug flow, stratified flow. And you can well imagine if that's happening, you might actually not see what is really happening in your pipeline at the specific at the 1/3 of diameter of your pipeline. So that's very important, and it's very important to understand these behaviors in both gas and dense phase to make sure you design a proper system. And there is ways to actually achieve that, but I think first comes to the understanding of the actual behavior of it. If we go to the next slide. The second is sample location. We see that go wrong a lot of the time. And firstly, of course, we see that the homogeneity is expected, but it's not always there. But then the sampling location, there's also standards for this. How far you stay away from a bend or a turbulent, a cause of turbulence in your pipeline. That is very important. A normal rule of thumb is 5 diameters away from a bend. And that's important because a lot of what we see, a lot of people still expect that I'm sitting next to a bend, so it's nicely turbulent behind it, and I can capture the components representatively behind it. But the opposite is true. You can well imagine a Formula One car. If you drive through a curve, the heavier elements get pushed to the outside. So those you might unrepresentatively capture if you directly capture it behind the curve. So minimal 5 diameters away, ideally 10 diameters away from a potential turbulent source. That differs, then there's a big difference between vertical and horizontal sampling. Also, whether it's downward vertical or upward vertical, those matter quite a lot. We go to the next slide. And then we come to the actual design of the probes itself. It's important that to be isokinetically sampling, the extracted flow should be at the pace or at the velocity of the flow inside the pipeline. If you are not doing that, then you can have two effects. Either you're undersampling or you're oversampling, and you see that nicely illustrated on the figure on the top and right. That means that either you're getting too much into your sampling and analyzer system, or you're getting too little in your analyzer system. And that can have significant effects in terms of underestimation or overestimation of what light components or heavy components are there. We see in different industries, so not CO2, but in oil and gas, that these can have very significant effects and really significantly impact what you are seeing in the end in your analyzer and in your samples, and really significantly overestimating impurities or underestimating them. And in the design of the probe, also, it really matters how isokinetic. It's not as simple as just designing a 90-degree probe. That creates unisokinetic behavior. It shouldn't be an obstructed view. It also had a whole design inside the probe. Also really matters in terms of how representative you can get the sample out into your analyzer and conditioning system. We go to the next slide. And then the next phase is, all right, now you've got your sample, you're sending it through your piping or tubing. And then if you want to bring it, and the idea is for a offline analysis, you bring it directly into a constant pressure cylinder. So you maintain it under the pressure of the line so that you can then, in the lab conditions, take it apart and really get a full good idea of what is in that pipeline. But if you want to bring it to an analyzer, it's critical that you condition it properly. Because most of the analyzers can actually not analyze it under supercritical or under the high pressures, under the temperatures that are transported in your pipeline. So that means you have to bring down the pressure and temperature in a regulated way to make sure you're moving to the phase that you can actually analyze it, so mostly at room conditions. And that is extremely important, because as you go through the phase curve, as we'll talk to later as well, effects can happen to the impurities. Things like adsorption, desorption. One is typical wall phenomena. Impurities can start sticking to the walls. And therefore you might not see them, or you probably won't see them in the samples or in the analysis. You can have chemical adsorption, so ionic bonding, which are not fully reversible, so you won't see them, so you won't see things in the phases that you would expect them to. And physical adsorption, which are reversible by a decreasing or increasing temperature, but you probably won't do that if you bring it back to the analyzer. And these are extremely important things to get right, because otherwise you are not seeing what you want to see. And also it's good to recognize that some of these analyzers have filters to protect the analyzer themselves. The fact that they have filters in them means you're filtering out something that you're then also not measuring. So it's very important to be cognizant of these things when considering impurities. Let's go to the next one. And this shows basically what to the right what happens. So you have a fluid or a gas in a certain phase, and to be able to measure them, you have to bring them back to a different phase and to different temperature and pressure, and you have to do that while not going through the phase where it can basically the supercritical phase where it can change behavior and suddenly expand. So you have to do it in a conditioned way, and you have to really be careful around elements like dropout, phase changes, and Joule-Thomson effects. We can go to the next. And if you do all of these things right, you get a right answer. But it's very important to recognize that if you do one of these steps not right, so the mixing or the sampling or the transport or the analysis, then effectively you're looking at an error or a deviation. So it's not a question of buying the best sampler or the best analyzer in the world and then getting the right answer. You have to do all the intermediate steps right to get a representative answer. And that is very important to recognize that it's not that it's basically a full integrated view on the system itself and the flow conditions and the conditions in the pipeline that you expect to be able to get the right answer. And do that over time as these industries are scaling up. So let me give it to Mano. Thank you.
Thanks, Gordon. Next slide, please. I will build on what Gordon explained, like how the sampling is very important, like in order to get homogeneous sample, representative sample. So I will build on that and explain how to get accurate measurement of a CO2 and how the gas metrology supports accurate analysis of a CO2. This slide is full of a lot of terminologies. If you look at a central part, so there are three key aspects to get accurate measurement of a CO2 is important. One is primary gas standards or primary gas mixtures. So then that links with analytical methods and then sampling, as what Godot explained. So they're kind of cycling loop. So we will be always doing this cycle to get better and better at what we do to support measurements of CO2 purity. So to begin with, if you look at the left side of that cycle, you prepare a gas standards and then understand gas standards lifetime itself, and then develop a methods. So then once we develop a method, what you do, you need to validate. Once you validate, so then you need to look at various sensors or various analyzers that has been put forwarded for measuring CO2 and then validate them. So once you do that, is this emerging field, and we've been looking at various scenarios, various CO2 stream. So you do get various impurities which are not before, or which are not known to us before, or which were not important before, but they become important at some point of time. So then we need to do this exercise again. So this is kind of a cycling loop. So overall, what we do, we standardize everything, making mixtures, developing analytical methods, and as well as doing sampling. And this is kind of how you can do accurate measurements of CO2. That's how gas metrology is going to support this area. So this standardization is also leads to standards development, both in IS1 as well as some committees. So that's what people are looking into this data, so that we have some sort of standards. But in the absence of that, I think what Energy Institute did to make a good practice guide, so that people in industry can use this guide and do analysis. This is just a summary of how the gas metrology supports CO2 measurements in accurate way. So go to the next slide, please. So in order to do gas metrology, we said primary reference materials are important, and then we also said certified reference materials are important in the guide, and how these can be used in the gas analysis. So before going into any of that, I will just explain the pyramid of hierarchy in gas metrology or gas analysis. If you look at right side of the slide, you could see a triangle where you have a hierarchy of a gas analysis. At the bottom of it, you could see gas analysis, where you do routine gas analysis by gas operators or gas laboratories. So above that, calibration gases providers will sit, which is equivalent to products or instruments developers or manufacturers. So everything below that will be using those calibration gases. For example, calibration gases will be provided by industries like Lind Ehrlich to gas analysis laboratories to calibrate their gas instruments as well as the results. So in turn, those calibration gas providers will be looking at national metrology institutes, something like for primary reference materials. In the UK, NPL is providing those reference materials. So across the Europe and around the world, we have many institutes who can provide these services to these calibration gas providers. So in terms, NPL traces its traceability to SI system. So in this case, we just put it as a mole because we measure CO2 in the mass. So that's why it is SI. So that's why this traceability runs through. So if you look at what exactly primary reference materials at the left side of the slide, so which underpins the measurements and traceable to SI standards. So these can be used for developing analytical methods, calibrating measurement equipments, validate the results that you get. And not generally, these primary reference materials will be held at NMIs or National Metrology Institute by individual countries. So which will be then passed on to calibration gas providers. So this is an example, as I said, NPL is responsible to maintain gas standards within UK, and it's similar to in NIST is similar USA. Probably it's the same for VSL in Netherlands. So give you specific examples. So once you have a primary reference materials, then you pass this knowledge and this traceability to certified reference materials, which will be primary reference materials. You develop these certified reference materials, and which will be again passed on to all the gas analysis down the hierarchy. So So again, like how can we use these gas? Primary reference materials are like certified reference materials in doing gas analysis. Typically, you need to use these things in order to get like confidence in the measurements that you do, and also reliability to prove the reliability and as well as accuracy of the measurements that you do for like purity analysis. In general, it could be any analysis that you do. So in this case, it's only CO2 purity as CO2 stream purity. Next slide, please. While doing this purity analysis or like CO2 stream analysis, there are 5 or 6 different like key points which are very necessary. This is what we think. The first one, as like I explained by previous speaker, it's accurate sampling. That is very, very important to begin with. And the second one is like having a primary reference gas mixtures or calibration standards. Then once you do this, then the question is like which analyzer I should use using it. So choosing a right analyzer is again like very, very important for like doing analysis. Once you choose that, you need to develop a method, and you need to make sure that method is like fit for purpose by doing validation of the developed method. So then you do method development, and then like I want to do like an analysis. But how do I know I'm reliable and my results are accurate? So that's why like what we do. So we do like something called a proficiency testing or like an inter-laboratory comparison. So I will compare with my results or my capabilities with like some other laboratories or some other NMIs. That's what we do generally at NMI level. So we call it a key comparison. So that's again important for like you to have reliability and like accuracy in your results and have the confidence. So this is generally what we do, but like for CO2 purity, we have additional challenge, which I'm sure like most of you are like aware of. So doing a gas phase analysis versus dense phase comparison. So whether we can like rely on gas phase measurements for like measuring what's happening in the dense phase. Because at this point of time, so we do have a capability, or at least we have a possibility of developing a gas phase infrastructure for analyzing components in gas phase. But like at dense phase, because like we don't have anything which we can measure at high pressures, around 82 like above pressures. So that's something that we all need to consider when we do doing like CO2 purity analysis. This is not part of this guide, but generally I thought it's a good like example to give other additional challenge where you need to consider while doing CO2 purity analysis. Next slide, please. So as I said, like the first thing is like a sampling challenge. So there are 2 scenarios. There are many other scenarios like we can consider where the sampling error can occur. One is sample contamination. So where you get like false positives, you may end up getting higher than like what you're expecting. So that could be because like you didn't clean your sampling vessels properly. There may be like an ingress of like air and moisture into your sampling itself, and other oils and like other contaminants from the process or like from the sampling loop entering into the liquid analysis itself. So in those cases, what you say, so you see like results which are higher than expected. So if you don't have like calibration standards, you tend to believe that like those results are correct. So other scenarios like where you get like false negatives. So sampling vessel suitability, for example. So there is like a lot of components which are really reactive and which tend to like adsorb to the vessels of either maybe tubing which used for sampling, or analyzer like parts, or it could be like a cylinder itself where you hold your sample. So in that cases, so adsorption over the surface vessels could lead to the negative results than what you're expecting or what's supposed to be like in the stream. So other possible scenario, which is more likely to scenario in CCS, is like inter-analyte reactions, because there is many possibilities that like various components react to give like products are like which we not expected. So without understanding of proper chemistry and proper like probe, we are not in a position to say like accurately like what's measuring is what it is. And the other thing is like sample stability itself. So which may not be like necessary for like online sampling, but like for offline sampling, this is key. Some samples may be like stable only for like couple of hours. Or some species may be stable for like years. But in that scenario, without like having a proper understanding of a stability of the samples, so you're going to get like false negatives. Just to give an example, like I have put a like right side. If you look at the right side of the slide, so I have plotted like a hydrogen sulfide storage stability with various cylinder types. So basically they have a different coating. So if you look at like some of the coating technologies, like leads to degradation of a sample completely around 10 days. So this is something that before, if you don't do all of this, there is no like, way we can figure it out, like why you're getting and what you're getting. So that is like something that you need to be very careful while you're designing a sampling of your system and sampling of the CO2 stream. Next slide, please. So other challenge, biggest problem within like, developing this primary reference material calibration standard itself is many people can come forward and say, oh, okay, we can provide like, these calibration standards. So the question that we need to be asking, or at least looking for, whether they're traceable, whether they're accredited. Those certified reference materials, if they're not accredited, they're as good as like, you're not using them. So then other challenges like, the compositions are like a really like, complex and bespoke. So we need to make sure like, we develop a fit for the purpose samples which for used for analyzer calibration and as well as like, for validating our results. And also like, uncertainty, again, this is something that I think we not agreed on. What should be the uncertainty of the measurements and what should be the uncertainty of the primary reference material. That's where you start all the uncertainty feeding into your overall like, measurement of purity of CO2. So that's like something that if you don't stick or if you don't fix to that, achieving low uncertainties is always a challenge. And so if you have a really like, low uncertainties, then that's really going to be problematic for developing these measurements or primary reference materials. So the biggest problem that what we experience or what is that everybody should expect is like, non-standard behavior of a CO2 itself. So because like, it has a very difficult or like a very challenging pressure, temperature, like, phase diagram. So you may not be able to like, have a lot of freeway as opposed to like, natural gas or like, hydrogen or like, any other gas. So here you need to be very careful in designing these primary reference materials. So pressure and temperature is very important. Otherwise, you end up getting unstable mixtures. This is our experience. I'm sure like this is like, it needs to be considered while developing these calibration standards. Next one, please. So what we do typically, this is a simple slide. So we develop a primary reference material gravimetrically following a ISO standard. And then our standards are like, traceable to SA system. And then primary reference materials ensures the measurements are traceable and accurate. Yeah. Next slide. So other difficult problem, like, when we come to like selecting analyzers, we have been here a lot of people saying like, oh, this analyzer is better over that, and this is like, it does a good job. So this is like being heard again and again and again from a lot of people. I mean, it's not like, everybody's exception to this in this field. So what we need to be considered, we need to consider like, number of analytes that we need to be like, analyzing, and like whether one technique is enough, or we need to consider many techniques, which may be like a more likelihood. And then use of appropriate calibration standard for that particular analyzer. And also like, we need to see what kind of analytical parameters one has to be checking in order to like, use that particular analyzer, like a linearity, sensitivity, or like, metric gas. Again, like Andy has highlighted in the beginning. So it's very, very important to calibrate these analyzers with the representative metric gas rather than using like, SO2 in nitrogen. So it's very important to use SO2 in CO2 matrix to calibrate, to measure the purity of CO2 in like, stream that we're talking. Then other thing like it is important is like, analytical method validation. I'm going to explain that in the next slide. Sorry. Okay. So yeah, this is just tell you like, one example, like where we fight always like, one analyzer is better over the other, but like all the analyzer needs to be considered, and like, we need to consider based on the merit. We need to be in a position to understand what the advantages and disadvantages of different technologies or different techniques together. If you talk about online and offline analysis, when it comes to CO2, we are talking only online measurements, but it's very, very important to measure or like, validate those online measurements in a periodic manner with offline analysis as well. Without doing that, we will not have in a position to accurately say our online measurements are like, accurate. So as like, listed in the slide, so they have both advantages, disadvantages, but I don't go into detail, but like it's something that we need to consider. So one technology is not better than the other, but like it's a like, a decision that we need to make based on the need and based on like, what parameter we're operating. Next slide, please. Okay, maybe you can put press. Yeah. Okay, so how do we develop a method? Sorry. Yeah. Generally, like, yeah, we use a traceable PRMs. So people down us has to use a certified reference materials. We use like ISO 6142 method. So people are open to use this, or maybe equivalent method should be followed in order to develop a method. So once you develop a method, you need to check various analytical parameters. That analytical parameters again defines your application end purpose. So you could check LOD and LOQ, linearity and working range, trueness, selectivity and interferences, so precision, robustness. So various things it again comes to what is the end result that you want to get out of this method development. So then once you do all of this, so it's very, very important, probably key to all the measurements to have uncertainty. Without uncertainty, I think any results cannot be considered, because without uncertainty, your results may vary anywhere. So we, as NMI, we say uncertainty of any measurement is very important. Without uncertainty, we don't accept any measurements. So there is GUM, it's a guide for measuring expressing uncertainty in the measurements. So it's a very good guide. So I welcome people in this area to go and read or go and understand how to develop one. Once you develop uncertainty, so the validating is like a last step in developing these methods. So we use according to ISO 17025 method to validate our on the analytical methods. So then it proves the method that you develop is fit for the purpose. If you go to the next slide. So there is a very good guide like a Eurochem, so which says how to develop a method. So in most of the times, we don't have to develop a new method, or we don't have to invent a new method. So what is there there is a method maybe where there is a chances of you modifying it with the existing little bit of a variation in the parameters. So you could develop. Then once you develop, evaluate the method performance. So if the method is fit for the purpose, so then go and issue the validation report. If it doesn't, then you need to relax your some of the analytical parameters. For example, if you're working with 90% accuracy as opposed to 95% accuracy, then yeah, you you control your accuracy as a 90% as opposed to 95%. Then, but all this needs to be reported in the method validation report, so that someone who is using this method understand what the method is and what the parameters they're working with. This is a simple flow diagram how to develop a analytical method. Next slide, please. Okay, good. Somebody has said they have standards, they have capability methods, everything fine. But I've just put a couple of questions slides here. One is I've taken from ISO 27913. And just to give you an example, what all the kind of impurities we're looking at. This may not be necessary for valid for this particular good practice guide, but just to give you an example, I've listed here. And let's say somebody says okay, we measure all of this fine, but how do we trust those measurements? So whether those accurate, do they have any technical evidence to back their claim? And then reliability. So do the measurements really accurate? So whether they're traceable or uncertainty is what the questions we need to be asking. To do that, as I said before, what is important is either you need to do proficiency testing of your capability with some host who has capable, or you do inter-laboratory comparison if you're working at NMI level. So that's what we suggest, and that's what we do on a routine basis. So if you go to the next slide, please. So I've just given one of an example, how do we rely or ensure the reliability of analytical laboratory measurements. So there are simple steps. One needs to use calibration standards. Those calibration standards has to be certified. Then you need to have an inter-laboratory comparison. And then the host who is do this inter-laboratory comparison has to be accredited and capable of performing assessment independently. And then there should be method validation report. So if you look at bottom of the slide, I'll just give an example. So what we do, we make a reference materials, then we send our reference materials to various NMIs. So you can consider a scenario where you could do one, you can check the stability or accuracy of our reference materials, or we could also be checking analytical capability of the labs which are present across the globe, which are part of the comparison. So that's how we do. And then once we do this, so we'll get understanding of each other's capabilities in this space. So I have given just example, one example, we're measuring water in hydrogen. So if you look, there are 4 different labs which performs analysis, but you could say at the top right corner, there is a result, but it doesn't associated with it. So it means that results cannot be reliable. So other results at the bottom left, it is too far away from the true results. So those two labs you cannot trust to do analysis. So this is how you can maintain the proficiency or capability of a different labs. Next slide, please. Yeah, so as I said before, so this is not part of this good practice guide. You can press maybe one more time. So we did just finish one of this project with comparing our gas phase measurements with the dense phase measurements to see whether we can measure dense phase CO2 with the gas phase. What we did, it's very simple. So you look at SO2. We made SO2 in a CO2 mixture. So the mixtures we targeted were 50 ppm and 1 ppm. So we prepared from pure SO2, so two different sets, prepared by two individual operators, not by same person. So we prepared two different sets, and then we validated two different sets in a gas phase. So once we do those gas phase measurements, what we did, we pressurized those samples to up to 80 bar, so that you essentially converting them into liquid phase or a dense phase a CO2. So then once you convert those into 80 bar, but then when you analyzing, essentially feeding that back into analyzer around 5 bar pressure. So it means we wanted to check how good the homogeneous sample you can get back when you do these kind of a measurements, because we know what is the measurement and what is certified value at gas phase measurements when we do. And then once you pressurize to 80 bar and then re-measure those samples, then you see what's the difference between measuring at gas phase and dense phase. How it's a kind of a mimicking an example of you're taking sample from a CO2 pipeline, measuring in analyzer, which is maybe 2 to 3 meters up away from the pipeline, where the pressure is drastically reduces compared to the pressure in the pipeline. So that's what we did. And if you go to the next slide, there are two significant observations that we made. The first one is a stabilization of the signal. So signal used a lot of time to stabilize, because it's we spend a lot of time to get consistent results. So repetitions, we need to get at least we have a minimum quality within our NPR, how many repeats you need to do. So to get those stabilized repeats, it took a lot of time for us at even at 20 degrees, 20 bars. So then if you look at a result itself, I've just plotted percentage difference of various amount fractions with respect to different pressures. You could see there is a lot of variation of 0 is nothing but gravimetrically expected value. You can go up to 25% difference in SO2 amount fractions. So various D numbers are nothing but various amount fractions of SO2 in the stream. So we're still trying to understand what's happening here, and then how we can accurately measure, or at least is there possibility to measure dense phase CO2 using existing gas phase analyzers. So that's all from my side, and these are all the various challenges one needs to be considered. These exact results. Next slide, please. So this is within the guide, there are various analytical methods or techniques has been reported, and also various detectors. So I'm not going to read all of them. All of these have potential to be used in a CCS context, but this needs to be checked and verified. And as we always pressing, you need to compare against standards, and then method needs to be validated before these techniques can be employed for analyzing various impurities in the CO2 stream. Next slide, please. And then finally, what is that most important for doing a CO2 analysis? So you need to make working against PRMs or CRMs calibration. Ensure that this is calibrated in a representative matrix, not using either air or a nitrogen matrix. That's not going to again give you accurate results. So then you need to checking various analytical parameters. That would be limit of detection, limit of quantification. You can have a minimum number of analytical criteria to check that based on what is the outcome that you're expecting. In many cases, you may need two analyzers in antiphase, and one analyzer may be capable of measuring many impurities, which may be ideal situation, but in reality, we may have to consider different analyzers. And presence of some of the impurities can mask measuring the other impurities, interference. So these are all the things that we need to consider in order to have an accurate measurement of CO2. I will hand over next to Andy Brown.
Thank you, Mano. That's quite a lot for us to take in. Before moving on to the next bit, I'd just like to comment that the explanations, the descriptions you've had from Goddard and from Mano, those are more comprehensive than is in the paper. But it's nevertheless important for people to understand that this is quite a complex technology. It's not just a question of plug and play. Can we move on to the next slide? So what we have done, is we looked at 29 different impurities and we considered 26 possible techniques to measure them. And we've done a RAG analysis or a RAG presentation of what's possible. So if you look across the graph here, you can see some of them are shaded green. And if it's shaded green, that means that effectively you can go to the shops and buy this equipment, and that would be suitable for application. If it's got a green with a question mark in it, it means that the equipment is theoretically available, but the reference materials, the primary reference materials that Mano was describing, are not available to calibrate the equipment at the sort of levels that we're talking about. And if you look at the table there, you discover quite a lot of them have got question marks in. And that leads us to one of the conclusions that we'll come to in a minute. If it's amber, it means it's potentially available for CCS applications. So that says that the methodology should be able to detect it, should be able to work, but is not currently, as it were, being offered. And if it's red, there are good reasons why that equipment is currently unsuitable for measuring the impurities in CO2 streams. And the reasons behind those are in the preceding sections of the report. And this information has been gleaned from several manufacturers of equipment. And this is probably a good opportunity for me as the principal author to express my thanks and gratitude to each and every one of them that's contributed to it. There are other numbers in there that you will see, and that refers to other limitations in what the equipment will be able to measure in practical terms. So you can see there's quite a lot of just looking at that. There's quite a lot to digest there. Can we move on to the next slide, please? So I said at the beginning that we wanted to carry out some sort of a gap analysis to provide us so that we know what we don't know. And it's obvious that we're going to need a full suite of accurate and traceable primary reference materials, as Mano was describing. And that, as you'll see from that sulfur dioxide in carbon dioxide presentation there, that is quite a lot of work to do that. And that is just a binary mixture, two components. We may well need to do this for several components simultaneously within the CO2. And very quickly you can come up with some very large numbers. We need to develop accurate and fit for purpose analytical methods so that we can have confidence in what we're doing. We, again, Mano referred to the stability of PRMs and looking at things like what container you put it in, what the life of it is like. So we need a proper stability study doing so that we can get the best information possible. Then there is the necessary but tedious testing and validation of analyzers online. And that's going to mean rigs and test rigs being set up. It's going to mean that manufacturers have got to produce the equipment and offer them for testing and validation. And having done that, there will be some sort of certification process that goes with it. Goddard has explained to us the problems involved in making sure that we get accurate sampling and making sure that we are really getting a representative sample. And I wouldn't underestimate the work that's involved in being confident that we are actually sampling what we want to sample. And the last one is a bit of a killer because there are lots of standards out there which will tell you how to calibrate measurement equipment for looking at impurities in natural gas, in petroleum spirits, in all sorts of things. But there are no standards that will tell us how to calibrate the equipment in a CO2 matrix. Those have got to be written. Now, standards typically take about 4 years to produce from scratch. And there is a CEN working group, a part of TC 474, a working group 3, which has made a start writing these standards. But the reality is that if they come up with a standard in 2028, then that is going to be too late for some of the Track 1 projects in the United Kingdom. So we have formulated a strategy that we're hoping will be a stopgap for that. Can we have the next slide, please? So are all the impurities of equal importance? And this is very subjective, but the priorities would appear to be as listed here. Part of these are, and amines is a very difficult one because there are many different amines. So just looking for a particular atomic structure or molecular structure won't necessarily cut the mustard because you may be looking for a primary amine, whereas the equipment is calibrated more towards secondary amines. So that's quite a difficult one. Perhaps the most difficult one, which isn't listed because it's that of ammonia, because ammonia will dissolve in the carbon dioxide. So that is a particularly difficult one to measure. But there you are. And the timescales are, we really need this to meet the Track 1 project requirements, which effectively means that we need to pull our socks up and make a start soon. So it's hoped that now we've stated the gaps and given them some priorities, we can now look at how we're going to plug those gaps and work down that priority list. And that, I think, is where tomorrow's problems begin. So thank you very much for your attention in this. Do please avail yourself of a copy of the full report. I think we can now hand over to Eva to look after any questions that we might have. Thank you, Eva.
Thank you very much, Andy, and thank you also to Goddard and Mana for these really interesting presentations. We have made it to the Q&A section of this webinar. So if you have any further questions that you would like to ask to our presenters, please put them in the Q&A chat. And I will read them out when they come through and direct them at our presenters. Maybe firstly, we had a question coming through regarding access to the paper. If we can have a look at the next slide, please. This is the website you're looking for. This is our publication website, the Energy Institute's publication website, where you can download this document. You need to log in for it, and it is unfortunately not free of charge, but there are discounts available for individual members and company membership. So do make sure to check that whether that applies to you. Next question from James Hewitt. Will clusters of CO2 suppliers make measurement and analysis even more complex, especially in relation to attribution of liability of problems? CO2 supplies from sources in a cluster may be heterogeneous in scale and competition, and quantities may fluctuate. Anyone who feels particularly drawn to this question?
Do you repeat the question, please, Eva?
Yeah, will clusters of CO2 suppliers make measurement and analysis even more complex, especially in relation to attribution of liability for problems? So this is around really CO2 clusters and how working within a cluster would make everything a bit more complex. There's in addition to it, a cluster might be dominated by a larger power station operating dispatchably as well.
I can probably take this one. The UK Network Code requires this sort of analysis at the point of custody transfer. So and it also requires for transparency across the network so that the shipper can see the composition of the CO2 at each custody transfer point. So if one person starts to go out of spec, it is obvious as a result of the readings that we're taking who it is, and who, if you want, should be on the receiving end of a phone call to say, your oxygen level is higher than permitted or whatever. So I think that sort of thing is covered within the provisions of the network code.
Fantastic. Thank you, Andy.
But it's a good question.
Yeah, indeed. Next question. Are you also considering the measurement of impurities in liquid phase, i.e. for non-pipeline transport? So I suppose it's in the guideline.
Well, I'm sure Mano will correct me if I'm wrong, but at the moment, gas analysis equipment will only operate at low pressures, and by that I mean probably no more than 2 bar. So this is the relevance of what Goddard was saying about having to take a high pressure sample to warm it, and then to reduce the pressure of the hot CO2, and so that we don't get any dropout along the route. It is one of the items for development to be able to look at the impurity content of dense phase CO2. But at the moment, the focus is on accurate measurement of gas phase CO2.
Yeah, you're right, Andy. I mean, whether we building measuring or not, it maybe I put this question slightly, whether we have enough capability to measure is what we're looking at. So once we have enough confidence in measuring all the impurities of interest accurately, then obviously we need to focus on dense phase, probably even like liquid phase if somebody wants to operate in liquid phase.
Right. Yeah, related question to that from William Ritchie. Is dense phase CO2 expected to exhibit different flow regimes, or is it expected to be isotropic?
I'm not sure, I would make a justice for that question because my background is a chemist and measurement science, probably someone with engineering, a process engineering background, maybe Andy or maybe Codert can answer that.
I think there's going to be a lot of tests on that, and I think it's going to be the key question that does it behave as one phase, and it's going to be really vital to actually test that, because I don't think nobody really has the answer yet on that, which is why I think as some of the projects in Norway, Northern Lights have such a really tough requirement when it comes to impurities, or what goes into it.
Fantastic. Thank you so much. There's one question whether there's a contact to join the committee to test method development. I will just drop my email address in the chat, and then that anonymous attendee can just reach out to me about that. Are there any more questions from our attendees today? Otherwise, for the moment, one question that came through as well was about how to ensure analyzer performance, especially around linearity and sensitivity across trace and high concentration impurity ranges, particularly in complex matrices. Mano, do you have a view on that? How to ensure that?
Yes, I mean that's something that's actually we need to be really careful about because online analyzers often drift, so that drift needs to be corrected. So and also as I said in one of the slides, so you need to make sure you do periodic offline measurements in order to compare the performance of the analyzers online. So if you do these on a periodic basis, I think you ensure that measurements are accurate. So that's the only way you can make sure measurements are working. Otherwise, again, as an end user, we need to be asking a question because, people told me several times that, some of the analyzers are drift free, which you need to be quite, accept this with a pinch of salt, but you need to be always asking a question: is that true? What's the evidence for that? So we need to be very careful. And most of the analyzers often drift, so that drift depends on what's flow in, how stable or how rugged the system is. So we need to have that data and evidence in a periodic manner to make sure the analyzers shows the accurate results. So that's the only way we can ensure that they're drift free.
Fantastic.
Eva, can I just mention that in the report there are tables which relate to a particular impurity, and there's quite a lot of gaps in these tables. This is information that wasn't available at the time of writing the report. And what this committee would like to do is to initiate an update of the report in fairly short order, so that hopefully we can fill in a lot of these gaps. It's also important that as manufacturers start developing the equipment, and as people like NPL start to access primary reference materials, that we keep the report up to date, so that then it will be useful. No, out-of-date information is not any use to anybody. So for those people who are actively interested in the topic, there is an opportunity to shape the next version, which we are hoping to be starting to look at before too long.
Absolutely agree, Andy. Thank you for raising this. So really a call for everybody on this webinar. If you're interested in this, if you have expertise in this, do reach out to me. I'll drop my email address in the chat, and we can see how we can get you involved in the relevant working group, which will work on updating this guidance in hopefully very shortly. I don't have any more questions. So I think this is a good time to wrap this up. We're sort of at the, what was it, 70, 75 mark minutes. So I think this is a great time. Thank you very much to everybody who attended, and especially to our presenters, Andy Goddard and Mano. This was a really, really good, really interesting webinar expanding on the recently published CO2 stream impurity measurement guide. The recording of this video will be made available in due time on the EI's YouTube channel. So if there's anything you wanna see again, or just check out again, have a look out for that. And with that, I think we can close it. Final thank yous to Amy Jane Lewis and Srija Roy for hosting us and for running the technology in the background. And yeah, if there's any questions, you can drop me an email and I will send them the right direction. Thank you very much, everyone. Speak soon.
Thank you, Eva.
Super.
Thank you.
Thank you. Bye-bye.
Thank you all.